Okay, so before we talk about the next few results in number theory, we're going to talk about a special function first called Eulers Phi Function. And you may also know this as the Eulers totient function. And we've already actually defined it in a previous example in this course. But let's go through another small example again with a concrete number, just so we can see what this function is doing. So how many integers in the set 1 to 10 are relatively prime with 10? Okay, so let me just list all the numbers from 1 to 10. Okay, and we just go through each one of them. And if it's a number that shares a factor with 10, so 10 is 2 times 5, then we remove it from the list. So 2 shares a factor of 2, 4 shares a factor of 2, 5, 6, 8, and finally 10. And we are left with 4 numbers, right? So the answer here is 4 integers. And this is the output of Eulers Phi function evaluated at 10. Right? So it's a function that, given an input, that's a natural number, it outputs exactly this number. Go through all the numbers in the list from 1 to 10 and count those whose GCD with 10 is equal to 1. Right, so how many are there? And we'll see some application of this later on when we get to what we call Euler's theorem. But in this video, let's talk about the phi function in more detail. In fact, that's the definition, right? And I don't know why this is the symbol here. It should be k in the natural numbers, right? So it's the cardinality of this set, the set of all natural numbers from 1 to m that are relatively prime. And it's a nice exercise to start listing each one. And I don't know, just for fun, you can do it, right? But let's work on generalizing this. Like, for instance, if you know that the natural number you have is a prime number, well, what can you say about the phi function evaluated at p? And just by the fact that it's prime, it means, well, it has no other factors, right? Other than 1 in itself. This means all the integers from 2, 3, 4, and so on until p minus 1 are relatively prime with p. Right? In fact, 1 is also relatively prime with p. And so, how many are there? Well, there's p minus 1, right? So it's all these integers. Right? Essentially, when you start listing all of them down, you're not going to be able to remove anything from the list, right? Because they're all co-prime with p. And in fact, this statement here basically says if p is prime, then phi of p is p minus 1. So you can think about this yourselves. If I tell you that phi of a given number m is m minus 1, can we conclude that p, or well, that m is prime? Okay, so try thinking about this, how you prove that statement. But I'll move on though, and actually give you a general formula for computing phi of m. This is actually something you have seen before when we talked about inclusion-exclusion. right? You just have to basically look through each prime factor of m and start removing integers divisible by p1, p2, and so on until pk individually, and then adding back all integers divisible by pairs, right? Products of pairs of these factors, and then subtracting triples, and so on, right? So your typical inclusion-exclusion routine. It turns out that this expression here can actually be rewritten in this form. And this is actually something that's easier to evaluate for us. Right? I'm not going to work through the details there. Right? But as a first step, you may recognize that this formula for phi of m actually is the following. Well, first of all, n doesn't really depend on the subset S that's indexing this summation. So n you can factor out of the whole thing. And what this summation gives you is, well, S is the cardinality. Well, the power is the cardinality of S. So if you're taking singleton sets, then it's -1, which means you have -1 over P1, -1 over P2, and so on till Pk. And then if the cardinality of your subset S is 2, then it's positive. So you're adding all the reciprocals of the products. Okay. And I'm not going to complete this sum, but you can actually show that you can rearrange this and get this and factor stuff out. Ooh, in fact, I forgot the 1 here. This starts with a 1. When you take S to be the empty set. Okay, so this formula is pretty nice here, right? And I'll give you an example. What is phi of 300? Okay, well, you just need to find the prime factors of 300. 2 is a prime factor. You can remove another 2. And this is now 3 times 5 times 5. Which tells me that 300, right, times 1 minus 1 over 2 times 1 over 1 over 3 times 1 minus 1 over 5. And the answer to this is, well, it's a half times a third, well, not a third, but 2/3 times 4 over 5. And you can compute this, and this is going to give you exactly 80. And that's phi of 300. And this formula actually intuitively makes sense if you think about it. If 2 is a factor of 300, then when you're going through that whole list of integers up to 300, then you have to remove all even numbers, right? Those that are divisible by 2. That's what this does. This tells me, let's keep half of the integers from 1 to 300. Similarly, since it's divisible by 3, when you're going through this list, right, 1, 2, 3, you remove 3. 4, 5, 6, you remove 6. You're removing every third number, which means we're going to be left with roughly 2/3 of what we have after you already remove half of them from 2. And finally, you're going to be left with 4/5 of what remains, right? When you remove every fifth number or every integer that's divisible by 5. Right? So I like this formula because it makes sense to me, right? You're keeping the fractions of m corresponding to these prime powers. And this is actually what the graph looks like, right? When you plot a scatter plot, phi of m, m equals 1 to 200. And in fact, this line on top, right, this line is very, very close to the line y equals x. And this actually corresponds to just all the prime numbers. And I sort of answered the question that I left you with a while ago, but it's okay, whatever. It's actually an if and only if statement. Phi of m is m minus 1 if and only if m is prime. And that's exactly all these numbers on this line. You can even check something else here that's interesting. If you look at this line, for instance, that's roughly the line y equals x over 2. Right? So 2,000 is close to 1,000, right? And these are basically all those integers, or all those natural numbers where you have 1 minus 1 over 2 as a factor, right? Where you've multiplied by half. And well, possibly some other large prime as well. And you get something close to x over 2. Right? Now, of course, the more prime factors you have, the smaller phi will be. Right? So these numbers, for instance, are divisible by many prime factors because they're down there.